Hello everybody. The sun, that amazing glowing ball of energy in the sky that gives us food, energy, shapes the earth and gives us the urge to procreate and reproduce our species, as you do. Anyway, it also is quite good for powering sheds, which is what I'm doing. I have recently managed to completely, well, more or less make my shed and my amateur radio station solar powered. And I say almost, so this sort of solar power is on a fairly low scale. It's not the same as converting your house to use solar power with the big 5 kilowatt installations with massive solar panels on your roof. Now this is more small scale, designed to power devices that use DC. So that would be like the likes of laptops, ham radios, LED lights, and computer monitors. They all, although they normally take a AC input, it all gets converted to DC. So those are ideal, and they also are fairly low power consumption, so they're ideal for what I'm doing here, which is basically using a small leisure battery to power my low power appliances. There's a tumble dryer in the shed, and there's no way I'm going to be powering that from a solar powered setup anytime soon, so that still means. But anyway, we don't use the tumble dryer very often because it sucks up electricity. So a bit of background, I've always liked to dabble with solar power, and I've got some I have got some used solar power in the past to power my ham radio field trips. Generally using small batteries like this. This is a 10 amp hour battery. If you're powering a radio that uses between 0.1 and 2 amps depending on the power output, this is kind of perfect. It'll get you a couple of hours. And it weighs about 3 kilograms. But it's not so heavy that you couldn't carry it in a rucksack. I just like messing around with solar. I don't have a particular long-term interest in it in terms of moving over to solar power. I don't think it's ready for the mainstream yet, but you can do a lot with it. I'm certainly not a survivalist or a prepper or anything like that there. No, for me I'm more interested in the technical aspects of it, and also certainly not in it for saving money, because I'll do some sums towards the end and you'll see why this ain't going to save you money. But anyway, let's get started. First thing I want to do is talk about generally the general layout of a solar powered system for what I'm doing here. So let's just say you got the sun, and that sends down its life affirming energy, and you pick it up using a solar panel. And let's do one of those solar panels that always has the little lines on it. And the solar panel outputs between 14 and 18 volts, although what matters in our DC setup is 12 volts, but I'll explain why soon, why there's a difference there. That goes into a device known as a solar charge controller, which basically regulates the whole system. It's sort of the most important part of this system. So let's say you got your plus, you got your minus, so a panel goes into there, and there'll be 3 sets of input outputs generally. Some other ones have do it differently, but generally there's 3. So you'll have the solar input, a battery output, and that goes off to your battery here. So let's just say that's your battery there, your terminals, plus, minus, and that goes like that there. And there'll be a load, so say that. There'll also be a load option. They generally show on the devices, they show a picture of a light bulb. Look at my terrible picture of a light bulb. Right. So really, it's quite simple. How it works now. The problem with the load option here is generally it's only useful for low power consumption devices such as lights or recharging phones or whatever. In most installations like this, I've seen people don't use it at all. Now, some charge controllers actually have built-in USB and 12 volt outputs. Here's one I've got, which I'm not using at the moment, but I plan to. And there's your 6 input outputs here. So your solar panel goes into these 2, battery comes out of those, and that's load. But you can also see on the front there's 2 USB sockets for charging phones or iPads or whatever else. And this also has a nice display to tell you what the current voltage is and the power consumption and the like. Very nice little thing. This was 18 euros off eBay. But I'll talk about solar chargers more in a minute. Charge controllers in a minute. So anyway, What generally happens is, though, when you want to take power out of the system, is unless you generally connect directly to the battery. So, and there's two ways of doing that. You might have a device that's okay taking 12 volts straight from the battery, say a ham radio, and ham radio equipment is generally designed to have a very wide range of acceptable voltages. Their sweet spot is 13.8 volts, but they'll happily take anything from 10 up to 15, so 12 is fine. So let's say, there's a ham radio, like that there. And you can connect directly from the battery to that. But if you need mains power, and that's probably what most people are going to need, you need a device called an inverter. And an inverter simply takes 12 volts and converts it up to mains voltage in your area. In this case it will be 230, 240 volts. And again, that connects directly to the batteries. So really, it's not that complicated to set up, really. So what you have is your solar panel goes into your solar charge controller. The solar charge controller controls the charging of the battery, and there's 3 stages to this. Don't worry about it. I'm not going to cover that in this video, maybe in a later stage, but basically it regulates the charging of the battery, makes sure the battery is always charged up but not overcharged, so the battery doesn't get damaged. It also conditions the battery, so it makes sure that, you know, the plates inside the battery are looked after. And that's really it. I'm actually, after this section of the video, I'll actually show you my installation so you can see it, what it actually looks like in real life. So it's that simple. Now, let's talk. I'll move on to now talking about the panel types. I'll keep it simple. There's several types of panels on the market. The most effective, the best one is what's known as monocrystalline. And you can sort of recognise that by having a uniform brown colour. They are considered the best, but they're also the most expensive because they're expensive to manufacture. The other type you'll see is, and you'll see a lot of, is polycrystalline. So if you go off to Amazon or eBay and start looking for solar panels, you'll probably see polycrystalline more than any other type. And they're cheaper to manufacture than monocrystalline, but you need a bigger panel to generate the same amount of power. But generally, you know, that's what people use. Polycrystalline tend to look different, but if you ever see panels that have like little squares with the corners cut off, repeated over the front of the panel, like sort of like that there, and you'll just like that there, sort of set up there, chances are that's polycrystalline, and also has a slight blue colour, which is generally what most people use. But if you can afford it, get monocrystalline. There's also string ribbon and polycrystalline and other types. Really, you don't have to worry about those. Polycrystalline and monocrystalline is where you want to be. And ideally monocrystalline, but if you can't afford it, polycrystalline will work just fine. So there you go. I'll talk about the size of panels you need later as well when I come to do the maths. And yay, everyone loves maths. Math, not even once. Batteries. Again, I'm going to keep it simple. For this, I'm talking about lead acid batteries. They're cheap for their size, for the amount of power they can hold. They're heavy, that's the downside. They're not good, you wouldn't carry them around. We typically basically car batteries. However, and this is the important thing to remember, is there are 2 types. There's the starter type, which is what you'll get in your car. And then there's the leisure type, also known as the marine type, or possibly the motorhome or caravan type. The difference between the two is a starter battery is designed to produce a high amount of current very quickly. So you're talking like 70-80 amps instantly. A leisure battery is not designed to do that. A leisure battery is designed to release its power more slowly. So I think most of them they'd start to heat up a bit, maybe at 5 or 10 amps. Okay, you need to look at the battery's data sheet to work, to see what type, what its maximum amperage is. But generally, they're designed to release their power more slowly. There's nothing stopping you using a starter type for a solar power setup, but I wouldn't recommend it because you run the risk of power surges, and they might not last as long, and just you really shouldn't go there, honestly. And also in terms of other battery chemistries, there's gel types, there's lithium types, there's all sorts of other weird and wonderful ones. Again, this is not a discussion for this video. They're getting into specialized territory there where you need specialized charging equipment, and you need to understand how they work more than lead acid types. Lead acid types are largely fit and forget. So what you really want is a sealed lead acid leisure battery. That's what you want. Typical cost for 100 amp hours thereabouts, taking that as a midpoint, you'll pay about 80 to 120 euros. So you can convert that into whatever your local currency is. So yeah, also another thing to consider is wiring. You're going to have to wire this all together. As a general rule of thumb, you want 2.5mm wiring. That'll handle up to 30 amps, so that'll handle any surges you get. And I also want to talk a bit about the solar charge, the actual charge controllers themselves. And here's one. Now there's two types: pulse width modulation and maximum power point transfer, MPPT. You'll see them described using the acronyms. This is a pulse width modulation type. It's the cheapest type. What that does is it takes the voltage coming in from the panel and uses a technology called pulse width modulation to reduce it down to 12 volts and put that into the battery. Yeah, I'm not going to explain what that means in this video. I'm trying to keep it simple for the layman. The other type is maximum power point transfer. A lot more expensive than pulse width modulation, but also more effective. And what maximum power point transfer does is it takes advantage of the excess voltage in the panel. Now remember, I mentioned earlier that most panels put out 14 to 18 volts, but the battery only needs 12. Well, that's because the panels are designed to always produce a voltage even when there's little sun. So that in order to produce some voltage even when there's less sun that's needed, their top voltage is higher than what you would expect. So it means that they're always producing something, even if it's only 1 or 2 volts. Now, when you reach a point where they're producing more than 12 volts, a pulse width modulation charger will just discard that extra energy. No, that'll be dissipated as heat. Whereas a maximum power point transfer charge controller uses some fancy electronics and an algorithm and some microcontrollers to actually take back that wasted energy and push it into the battery. So effectively, a maximum power point transfer solar charge controller will give you 20% more charging efficiency. So again, I'll talk more about that in the sums. So if you can afford MPPT, go for it. If not, pulse width modulation will do the job. What matters is if you've got limited solar panel space, you might want to go for the maximum power point transfer in order to give you the same amount of charge for less solar panel real estate. In terms of pricing, pulse width modulation, anything from 15 euros upwards on eBay. I've got a Steka brand, which is German. I got that for 35 euros from a company called RS Components, which is a decent components company. Maximum power point transfer, 70-80 euros upwards on eBay, up to 300-400 euros if you want to get a really high-end one from one of the specialist electrical components retailers. So again, it's up to you how much you want to spend. I will say caveat emptor applies. Buying a cheap one on eBay is a bit of a risk, particularly if it's from the Far East, because you don't know if they're going to treat your battery nicely. No, if it charges the battery poorly, it's going to do damage. So just bear that in mind. Just looking at my notes here. So yeah, one other thing is I want to talk about is inverters. They'll take you connect them directly to the battery and they give you a mains output. Now, they come in various wattages. So the one I have attached to my setup is 150 watts, which I'll show you in a minute. You also get 300, 600, 1000 and 1500 watts. Generally, you pick the one above what you need. So if you're powering, say, a laptop and a monitor, that's going to be about 100 watts. You'd get a 150 watt inverter. The reason being is that inverters waste a lot of energy in doing the conversion. Typically 20%, and I'll show you this in the mathematics when it comes to it. If there's a lot of wasted watts, so like if you're using a 600 watt inverter and you're only using 100 watts, then the inverter's still making that change. It's still trying to produce 500 watts, so that extra 400 watts is getting dissipated as heat, and inverters can get really hot. That's normal. So you're just wasting energy. So you lose about 20% using an inverter. So, and again, price-wise, 20, 30 euros upwards on eBay. That's really, you can spend as much as you want, really. And they do look like car components because they're designed for cars, so they got the heat sinks now, so they look like fancy car stereo amplifiers that you see in boy racers' cars. Anyway, I'm ranting on now. So let's get on to the juicy stuff, the sums. And it's going to start to get interesting from this point forward. Okay, now the first thing you need to do is work out how much power you need. And I've got some. Let's keep it simple. Let's say you want to power a laptop, and I need a better pen than this. Never a good pen when you need one. Let's see what I've got here. Green. There we go. I'm in Ireland. So let's say laptop. Oh, sorry. And before you start, you should split your devices out into two categories. Ones that will be powered through the inverter, and ones that will be powered directly off the battery. A lot of people aren't going to be powering stuff directly off the battery, but if you do, keep the calculations separate, and I'll tell you why. A laptop, 60 watts, and I know that because the manufacturer's plate on the adapter tells me the maximum is 60 watts. However, in reality, when I've tested it using a mains watt meter, which is one of these, oh, there goes that. Smashing the place up. Which is one of those. It's actually never gone past 56 watts. So, but generally overestimate for calculations like this. The monitor, which is a 23-inch LED monitor, uses 38 watts. And I have a compact fluorescent lamp that uses 10 watts. I could actually use an LED bulb, that would save a lot more. So that's the inverter. I also have a ham radio, an Elecraft KX3. And that uses 24 watts maximum. Typically it uses less. You should use. Well, that was weird. Apparently there's a maximum record time on my camera. I didn't know that. It's a new camera, so there you go. So anyway, I finished off the sums without realising, so here we go. I'll go for it again. Laptop uses 60 watts, monitor uses 38 watts, the lamp uses 10 watts, total of 108. I've added 20% on to account for inverter inefficiencies. That's the conversion from DC to AC and then in the inverter, and that loses you 20%. I know it's not the best way to calculate this, there's a better way, but this is mostly accurate and it'll do the job for what we're talking about today. I know some people's going to give off at me about this, but trust me, I'm trying to keep this simple. So, plus 20% is 129.6, let's just say 130 watts for argument's sake, using direct from the battery without the inverter, 24 watts. So 130 plus 24 means that we're using 154 watts every hour. 154 watts watt hours. Sorry, that's our power consumption requirement. So now we need to work out what size of a battery we need to sustain that. So we'll do that by converting it into amp hours. And what we do there is we basically say 154 watts divided by 12 volts, because we're using a 12 volt battery, gives us a total of 12.83 amp hours. Let's say 13 for argument's sake. It's always nice to overestimate as you go along. So let's say we wanted to use the shed for 3 hours each day using this equipment. That would mean we would need a total of 39 amp hours. Great. You might use it for more, you might use it for less, but that's generally what I would envisage for my usage of the shed. Now here's the problem. There's a little known issue that you may not be aware of, and batteries, right, aren't giving you the capacity they say they are. Now, I have a leisure battery that's 70 amp hours, so you may think, well, okay, 70 amp hours, that means, oh, you could use that, what, for 5 or 6, no, you could power yourself up for 5 or 6 hours each day using that if it was fully charged. That's not the case. And I'll tell you why, using this chart, which I hope you can see. It's something I worked out myself. And I'm going to zoom in a bit. There we go. A fully charged battery has 12.6 volts. And as you use it, the voltage drops. And that is the sign of losing power. So, at 100%, it's got 12.6 at 100%, 12.5 at 90, 12.4 at 80, 12.3 at 70, 12.2 at 60, a bit of a more drop there between 60 and 50 where it goes to 12.05 volts, and then 11.9. And then we draw a line. The reason we draw the line there is, and I've said maybe, you're getting into a territory where a lot of equipment will just not work. So if it's 12 volt equipment, like the inverter, which requires a 12 volt input, around 11.9 volts and below, it's going to give off. It's going to start maybe sounding an alarm, or it might just shut itself down, but it's not going to be happy. It's not going to operate there. So between 11.9 and 11.60, I've called this maybe. That's when the battery is 13 to 20% capacity. Some things might work, some things might not. And 11.3 and below, nothing's going to work realistically. anything with any sort of circuitry in it. So basically what it means is if you want to be safe and secure, you work on the basis that you're only getting 60% of the quoted capacity. So if it says it's a 70 amp hour battery, you're not getting 70 amp hours. You're actually, let me see, we're doing my sums here. You're actually only going to get 42 amp hours, because 60% of 70% is 42. So what you have is a battery of capacity of 42 amp hours. Now, of course, you say, well, what about this 10 volts, this here, voltage and below, this 11.3, 10% and so on down? Can't you drain the battery till it's zero? You could, using, say, a light bulb or something like that there, but you risk damaging the battery and making it hard to charge in future. No, your battery's not designed to do that. It's supposed to, once you reach a certain level, you're supposed to recharge it. So, realistically, you only get 60% of what the battery says it's going to give you. So, in our case, if we want power for 3 hours each day, 42 amp hours is fine. It's okay. And plus the fact that we are going to be putting power back into it using the solar panels. So that's the Dahi! Stop it. Sorry, neighbour's dog. My dog wants to eat him. Yeah, so of course, like if you wanted to use more 4 hours, you'd simply say you would use 52 amp hours, and you'd need to get a battery that has capacity 60%. 60% of the stated capacity is 52 or above. So it's quite, the mathematics are quite simple, really. Now, let's move on to the charging side of things, and this is where things start to get a little bit more complicated. Actually, not really. Right. For charging, what you need to do is, first of all, well, in order to determine what size of solar panel you need to work out the battery watt hours. And to work out the battery watt hours is you take the voltage and multiply it by the amp hours, which in this case is, the battery I have is 70 amp hours, so that's 12 times 70, which equals 840 battery watt hours. So that's how many watts you need to pump into the battery to make it fully charged. So in order to work out how long you need, you take your battery watt hours, which is 840, and divide that by the wattage of your solar panel, which should be on a label on the back. In this case it's 50 watts, which is what I have, which gives you, and then you have to then multiply this by 2.5, and I'll tell you why. So that's BW, and that's panel watts multiplied by 2.5, which gives you 42. This 2.5, what's all that about? Well, you never get the full efficiency of any panel. So if a panel says it can pump out 50 watts, it very rarely does. Even if you're in a really hot area, you need to be pointed directly at the sun. If you looked at my video about solar powered phone chargers, power banks, you'll see, their solar panels can be quite picky about the sun and how much electricity they generate. So the 2.5 is basically a factor to account for the fact that they don't work. They very rarely work at the stated efficiency. Now, if you're in a hot, sunny area, you might, through trial and error, decide to lower that factor. If you're in a really, if you're somewhere that doesn't get any sun at all, maybe like, I don't know, like Strabane, or maybe somewhere like that there, you might increase it. But for the most part, 2.5 is what works for most people. And so basically what it's saying is we need 42 hours to charge the panel, charge that battery up using a 50 watt panel. Of course, we're never going to fully discharge the battery. You're only going to, like I said in my previous calculations, you're only going to be using 60% of the battery at most. Therefore, it won't take 42 hours in reality. That's the worst case scenario. Realistically, it's going to take 20 to 30 hours. So, and then you can redo the calculation using a bigger panel. So let's say you had a 100 watt panel. No. So that would be 840 divided by 100. Ooh. So that would be 84 divided times 2.5. Get my calculator out because I'm stupid. Which, oh, my calculator is crap. 84 times 2.5. Come on. See, I'm stupid. So 21 hours. So it's a half of that, so obvious. Now in terms of panel size, 100 watt panel is going to be about a square meter, roughly. No, if it's polycrystalline or a monocrystalline. You will hear people talking about something called solar insolation. And solar insolation is not really applicable to what we're talking about. Solar insolation is basically the principle that, well, it's not principle, it defines how much sun and how much energy is theoretically possible to be harvested that is generated by the sun. So basically says, in theory, the sun lands so much energy per square meter each day. So in the case of so for example, it might say it's generally by kilowatt hour. So Dublin, for example, where I live, in the winter, in December, potentially you have 0.88 kilowatt hours per square meter per day. So that means every day you take a square ground at sea level, and if you've got the best solar panels in the world, you will generate 0.8 of a kilowatt. In the summer, it goes up to about 2.6 kilowatts. The problem with the solar insolation is it's a good indication of how much sun you're going to get, and where to target for solar maximum solar efficiency. The problem is there's no solar panel that's that effective. So I mean that's the problem. Is there's like a 1 meter solar panel, like I said, is lucky to pick up 100. Maybe a top end solar panels might pick up 150 watts, not 880 in the middle of winter. So that's the problem. Is that the solar panels have limits. So this whole solar insolation thing is, you'll hear people talking about it and when trying to work out the efficiency of a solar system. It isn't really a very good calculation figure to use. For me, it's more a case of accepting the fact that solar panels aren't that efficient, so you have to overcompensate. Basically, that's what it boils down to. So anyway, so that's it really. I think I've pretty much covered everything. Let's just have a nosy here. No, I think I have, yeah. Like in terms of the mathematics, I hope you find it simple enough, and I hope I didn't bore you to tears, because I've been going on nearly 30 minutes just talking about sums. But with that, I'm going to finish up here and I'm going to show you my actual setup. Yeah, so here is the setup. The battery, there's your battery with the terminals attached. I meant to say in my earlier piece that you should really buy the connectors, these here. It makes connecting everything up a lot easier. But I'll come to that in a second. First of all, the panel in my very messy yard. It's a 50 watt panel, folds up into a suitcase. It's actually larger than it looks on camera, but it's 50 watts, does the job. I think it was about €80 in Maplin's, which is a UK chain. So here we are, let's take through what's going on. You can ignore this, and this. That's for a project in the future, which I'll cover in a later video. But anyway, so what we have is the solar panel comes in here and goes into that section. Comes out of there straight into the battery. Simple as that. And there's a light here to tell you what's going on. There's an orange light which is telling you the system switched on, and the orange light here, oh, it's just switched to green, which means it's now fully charged. Yay. And that comes out of there and up through here to the battery. I know I'm using brown cables and I should technically be using red and black to show polarity, but I'm being careful. So that goes straight into the battery. And out of the battery, also attached to the battery, is these two cables which go straight into the inverter. 150 watts, as you can see. And to show you in action, I will just switch it on and I'll plug in the compact fluorescent lamp. The odd thing I've noticed about inverters, the sockets tend to be upside down. I'm not quite sure why that is. I'm sure there's some logic behind it I don't quite understand. So switch it on, oh, and there we have light. I want to actually show you something. These inverters do get quite hot. So I'll just start off with this, 22, and as I talk I'll come back to it. Yeah, so really it's quite a simple setup. It works, it does the job. I can power a laptop from that, I can power the lamp, and I can power my monitor using a triple adapter such as that. Does the job. I suppose a quick word about cost. Right, here we go. If you're getting a 5 kilowatts home-based solar powered system, you're going to be spending anything from 15 to 20,000 euros, dollars, sterling, whatever, in your local country. It's expensive and it requires a lot of work. This is a lot cheaper. Solar panel, expect to pay 50 to 60 euros upwards for a 25 watt one, up to 150 for a 50 to 100 watt panel, and thereabouts. You can shop around and pick what suits you. There's absolutely nothing wrong with buying lots of little solar panels and connecting them in parallel, so long as they're all the same voltage output. So that's the main thing. As long as they're all rated for the same output voltage or thereabouts, that's fine. Don't connect them in serial, you'll have problems. Because then instead of having all having the same output voltage, you'll be adding the voltages up and you'll have no end of trouble with it. Everything goes, breaks up. The battery, I would say don't get anything less than 70 amp hour battery, being realistic. That was 75 euros. Again, 75 euros upwards for depending on the size of the battery. No, they're not that expensive. They're more expensive than regular car starter batteries, but they're better made and they're designed for a specific purpose. The charge controller, 15 euros upwards on eBay, or 35 euros upwards from a reputable brand bought from a reputable electronics retailer. And the inverter, 15-20 euros upwards again. So you can have a complete setup for 250 euros converted into your local currency, whatever that is, and you can power your shed and your laptop and your monitor and whatever else. Now the question is, will you save money doing this? And the quick answer to that is no, you will not. Well, you will, but it's not worth it. You do this more for experimentation, I think, or for the ability to take this with you and use it when you're camping or whatever. And I'll give you an example of why you won't save money. Remember earlier I identified that I used 154 watts of power every hour? Well, I worked out what that is compared to my mains electricity cost. And our mains electricity cost is 23 cents per kilowatt hour. So that means every 1,000 watts I use, I pay 23 cents. But 154 watts, right, means, well, if we take 1,000 for a kilowatt, divide it by 154, that means 649 is the answer. So if I divide 649 by 23, I end up with a cost of 3 cents per hour is what I'm saving by not plugging all the stuff into the mains. Which means it would take me a very long time to recoup the cost of all this gear. No, so you're talking like a long time anyway, no, years. So this is more of an academic experiment, really. You're not doing it to save money. Now, the home-based systems that have 5 kilowatt battery banks, yeah, you are probably saving a bit of money, but here you're not. So let's see if this has gone up. 23. 23. It's not working as I intended. I need to plug in something a bit more heavy duty. So let's just unplug this. So in the end I actually had to plug in a compressor to make this work and build up some heat. And the temperature is now up to 32 degrees, if you can see that. 31. So there you go. I suppose the takeaway from all this overly long video is that you can do solar power if you want, relatively cheaply and easily, and it isn't too complicated. All you need to do is get your sums right. That's the thing that matters most of all. Work out what you need, get yourself a battery that fits your needs, and have enough solar power, enough solar panels solar panel acreage to supply what you need for recharging the battery. It's all a question of balance. That's what it boils down to. So there you go. Hope you enjoyed it. I know I made mistakes, so go easy on me, but I hope that's been useful to people. Cheers. Bye.